do you want to know? What is it? Well, that's Dirac delta. No. So really, it's sorry, I'm getting my transcript thing and it's messing with me. Okay, so what is it really? Well, it's something that's not a function. It's a generalized function, if you will, or a distribution. And all this thing is it kind of acts like, so it's kind of acting like things that are in a family. I could rewrite it as, which way do I want to do it? I don't want to normalize that. It kind of acts like something that's in this family of functions that look like it's here 1 over n, and it's defined that for up to n, and it goes to 0. So if I wanted to write those explicitly, it looks kind of like 1 over n for 0 is less than or equal to x is less than or equal to n, and it's 0 else. So it's a function that, not really a function, but we still call it a function. But it's a thing that acts kind of like these, but in the limit. Oh, crap. Yes, you are. Yes, yes, you are. Very good question. Yeah, okay, there we go. Sorry, I'm used to switching between screens, and yeah, it was on last time I used Paint. Anyways, okay, so it kind of acts like this, but it's not this, right? And it's not really, like, you can't say it's the limiting factor of this, but it's really containing some of the stuff that this does in the limit. So in practice, what you need to know about Dirac delta is the integral from negative infinity to infinity of Dirac delta of x minus, so some point a. This thing is just going to be 1. Okay, so if I had a function here, f of x, this thing is just going to be f of a. Okay, that's basically all you need to know about it. Is it's this idea of, hey, I can talk about these functions here, which look something like this, right? Goes up to here and goes down to here. I can talk about these kind of impulse functions where I'm applying a force over a very small amount of time. Oops, wrong way. Oh, nope, not wrong way. Yes, wrong way. If I want n to go to small numbers, I want to flip this. You can define it that way if n goes to 0, but if I want to be consistent with what I think I did in the class, here we go. Okay, so this is a thing that has a force, finite amount of force being applied over a finite amount of time, right? So what you're really saying is, hey, if my delta t, which is really my 1 over n, if this thing goes to 0, what does the force need to be at that point 0 so that I get the area under the curve being 1? Functions don't do that, so I define this generalized function to do this. Okay, it's mostly for convenience, but you can formally define this thing mathematically if you want. It takes a fair bit of work, so yeah, it's kind of like the stuff that we did for Fourier series, that amount of stuff to get the convergence down pat. It's almost close to that amount of work, if not maybe harder math. Okay, so in physics and things like that, we want this concept here because we often assume that certain events happen instantaneously, right? So if something happens instantaneously and then bloop, something happens, like, hey, I have a particle, and here's a uranium particle, or yeah, atom or whatever, and boop, there goes a neutron. Like, how long does it take for the neutron to exit the atom, like the nucleus? Well, it takes no time. So you can use this as a model for that. Okay, so that's it. That's what you should know. Okay, and you should also be able to solve things like if I give you ay double prime plus by prime plus cy is y, there you go, is equal to delta of x, or like something more complicated where I have an extra forcing term, maybe a couple of deltas, x minus 1. You should be able to solve these. Okay, and to solve these, basically, you just take the Laplace transform of everything, knowing that the Laplace transform of this thing will just be your e to the, in this case, e to the x, in this case, e to the x, it'll be shifted, right? E to the x times your heavy side for both of these. But yeah, you can use that to chase out, and that's one of the properties that I believe is listed in your final cheat sheet. Let me check. That is previous thing. That's their midterm. Let me pull up your final cheat sheet. Assignments, final guidelines. Final guidelines. Did I put the Laplace delta here? Yeah. So wasn't Heaviside that guy. So if you just know that, you can literally do everything with Heaviside. So I've said a while back that you are getting this. You're not getting a cheat sheet you can bring in. You're getting this formula sheet. So the sheet that's available on Learn via the final section and then go to the guidelines, that sheet, this page here is what you get. So you get all the Laplace transforms you'd ever want, and you get the shifting theorem 1, shifting theorem 2, and in addition to that, you get convolution definition and convolution theorem, right? So like, So yeah, there's your shifting things. There's your convolution stuff. Okay, so you don't have to memorize any Laplace transforms. They're all there. Know how to use it, right? Like if you want to solve the difference equation that I wrote down before here, take the Laplace transform. Oh, you get this. Do your integration by chase it out and then go backwards. But yeah. Okay, I think that probably should be good for delta stuff unless there's a follow-up. No. So for the Fourier transform, you need to know that. It might even be a state the shifting theorem or state the shifting for Fourier transform or a is this thing correct type thing. Okay, so we're not going. So the thing there, we are not going deep into Fourier transform stuff. So I want to test you shallowly on it, and I'll test you shallowly in a way that if I were to give you the shifting thing type, or were to give you that, it would basically give you the answer. So make sure you know those ones and how to use them. So all you need is shifting, linearity, and the scaling formula. Memorize those three, and know how to use them, and then you're golden for how many points is that worth? Let's chase this out. So there's that number of points there. That number of points there. So if we compute this as a percent, wow. So yeah, if you know that, you're good for 6% of the final. Okay, so make sure you know those. Like it's the only thing I'm testing. That plus definition. So those are the only thing I'm testing you there on. So I'm hoping that that's like a free some percentage points, right? Yeah. So like as of now, things are still in person for the final. With I think so. Last I heard, there was supposed to be, don't cite me, but there's supposed to be a god awful for you guys makeup exam session where you take like 2 or 3 exams per day, every day at the end of the final terms. It might not happen, but that's what I saw being discussed at least. So as of now, things are still online. No. I'll just go out on a limb and probably say no. What our midterm was worth, what, 30%, right? Of the thing, and our final is worth 45 or yeah, 40%. So you need 35 out of those. So you need at least 5 out of 40, whatever that is. I can't do math today. It's been a long day. 40, yeah, so you need at least a 12%. So it's not possible to pass with the 6%. So if you got 100% on the midterm, that would give you 30% there. And if you got 30% on the assignments, that would give you 60%. So the bare minimum that you need is 12% on the final in that case, and then you would pass with a 72. Nope, it's already printed. You're stuck there, man. You got to know more than that. Yeah, so I can do that. I also did that in the recorded version that's uploaded online. So I will rechase it. It's probably going to be rehashing that, but make sure you ask questions to make it worth your while here. Otherwise, you could just watch the video I made. Okay, so I'm just going to do the same thing I did last time. Let me go to assignment number 3. Let me go to said solutions to assignment number 3. Let me go to and this problem I think is worth like 9%. Was it problem number 3? Where's the marmy? There's the marmy. That's a good kitten. Okay, so change initial conditions. Okay, so I believe this one's worth around 9%. I said it in the previous one. I can recalculate it if people really want to know. But yeah, so I put some pretty low-hanging fruit for the base. What's going to be, no, you have PD on the final. It's already, so the reason why you don't want it is because it, or the reason why I think you don't want it is because it really uses everything that we've done throughout this entire course. If you really wanted, you could use the Laplace transforms on this too to solve it. But yeah, it tests everything, so it's a really good test problem to see if you actually know what we've done. Okay, so here we'll have some PDE with some boundary conditions and some initial condition. I wrote this thing here just because I'm not going to deal with computing a Fourier transform or Fourier series there. Just, yeah, I can do a Fourier series separately, but I'll pick a nicer one than this one. Okay, so here we want to solve this. So what do we do? First, I'm going to take a drink because my throat is going to die otherwise. People actually showed up to my one office hours for 1:35. So I've talked 1, 2, 3. This will be the 4th hour in almost a row that I've talked. Okay, so the first thing you do is you say u is x times t. Okay, so here x is a function of x, t is a function of t. I'm not going to write the little t's just for convenience. Okay, so in this case, you plug this in. X does not depend on t. So when I take the time derivative, I get x t prime. Here, t does not depend on x, so I get mu squared x double prime t. Okay, that looks nice and dandy. Now I do, and I'm going to zoom way out, and I'm going to put a little mark there so I can actually access everything. There we go. Okay, so now what you do is you divide this whole thing out by mu squared. Make sure you divide by the mu squared. If you don't, you technically can still solve it, but if you forget to divide that by this because you don't know that you're supposed to divide by it, if you have one, it's probably going to turn out badly because it's pretty actually hard to fix it if you don't divide by the mu squared. Okay, so here these cancel, and here these cancel. Okay, so now that those cancel, I can rewrite this as t prime over mu squared t is equal to x double prime over x. This is of the form where we noticed before that our separation constant would look something like this. I don't know what it is, but I know it'll look like this where lambda is going to be some real number. Okay, so now what I do is I take the PDE and I turn it into two differential equations. X double prime is equal to negative lambda squared x, and t prime is equal to mu squared negative lambda squared t. Okay, split it into two things. Okay, so now that's what my PDE was. So now I want to solve these. Well, it turns out that my initial conditions, in order to satisfy it, I need a series. Yeah, there's all kinds of reasons why I don't start here. Well, one, you can't figure out what lambda is. So then I need to try to solve this, but if I want to solve a differential equation, I get a general solution unless I have appropriate conditions. So here I look at my boundary conditions. So I notice, hey, for the first one, I had u of x evaluated at 0t. Well, that here, if I take the derivative of it, would just be x prime evaluated at 0, t of t. And this needs to be 0. Okay, well, this term, no way that can be 0, because if it was, I have a trivial solution. And I can't divide by t over here, right? So this gives me a boundary condition that x prime of 0 is equal to 0. On the other hand, I have x of pi. That has to be 0 as well because, hey, I have a boundary condition here. Okay, so now that I have this, I want to solve this boundary value problem. Okay, I want to solve these together. And my goal for doing this is to figure out what is x and what is lambda. Okay, so if I want to solve this out, I first note, hey, the solutions to this well, x of x, I'll just write it for once, is equal to something times cos of lambda x plus another constant times sine of lambda x. Okay, so this is something you should be able to do in your sleep. It's solve that differential equation, right? Not bad. Okay, so everything depends on x, so the constants are just constants. Okay, so now I need to use the boundary conditions. Well, to do the boundary conditions here, I need the derivative of x. So I compute x prime of x. So here, this is simply going to be, well, derivative of sine is cosine, derivative of cos is negative sine. So minus a lambda sine of lambda x plus b lambda cos of lambda x. Okay, so now I have my choices. I can plug in this one first or this one first. Turns out using 0 is nice because when I plug in 0, haha, this goes away, so I don't have to deal with the lambda here. Okay, so if I do this, x prime of 0, well, sine of 0 is 0, so I get b lambda, cos of 0 is 1, so I get this. That has to be 0. So this tells me b is 0 or lambda is always 0. Well, if lambda is always 0, then over here, my solution becomes a constant, not necessarily trivial, but the only constant that satisfies the boundary conditions is 0. So if this is 0, I get the trivial solution. So lambda 0, I can throw it out in this case because trivial solution doesn't help me, right? So now I have to have b as 0. Okay, that's kind of sad-faced because I just got rid of one of the two things. So now I need to solve x of 0 is equal to 0. Okay, so x of 0, or sorry, I lied, x of pi. Okay, so I need to apply this. So if I plug in pi, well, since b is 0, the sine term goes away. So now this gives me a cos of lambda pi has to be 0. Okay, so I have two solutions. A is 0 or cosine of lambda pi is 0. So if a is 0, bad things happen again. Like, right? B has to be 0. Yeah, I can do a very quick overview thing. I'll finish this first, but if a is 0, b has to be 0, right? So that means things blow up and I only get the trivial solution. So this has to be true, right? So since this thing has to be true, what we do at this point is we say, hey, let's just look at when cos of something times pi is 0. Well, cosine looks like this, right? Blah. Bad drawing of cosine, but character works here. So this is pi over 2 where I have my first 0. The next 0 is at 3 pi over 2. Then the next one is at 5 pi over 2. So you can notice a pattern here, right? So I need lambda pi to be an odd number, so something that looks like 2n minus 1, picking minus just so that if I plug in 0, I start at 1, times pi over 2, right? All of these were divided by 2, all of those were odd. So here, oops, I'll do it with the red thing. So here, if I mark this out, lambda has to be that, okay? So here I can redefine and say, hey, lambda n has to be 2n minus 1 over 2, where n is some integer. Okay, that's my lambda n. That's one of the things I've wanted. The next thing, if I go back here, x will just be cosine of lambda n x. So my x's, I mean, if lambda are 0, what is cosine of 0? 1. What is sine of 0? 0. So my solution is a, where a is a constant. Can I write any arbitrary function as a? No, the only function you can write as a that satisfies the boundary conditions is 0. So you have no solution in that case, right? So if lambda is 0, you have a constant, and a constant doesn't satisfy the boundary conditions unless it's 0. Therefore, if lambda is 0, you're done. There is no solution. Like if you didn't have the possibility to have other values of lambda, then you couldn't find a solution, right? So you can't have this as 0 because if it was, you have a trivial solution, right? And you have to avoid trivial solutions like the plague. Yep, hopefully that helps there. So my x function would simply be cosine of 2n minus 1 over 2 times x. And here I dropped my constant because I don't need the constant. I'm going to add it later, right? I'm going to use linear superposition, so don't have to carry it. I just need a family of solutions. Okay, so this is my entire goal of finding. This is what I wanted to find for this problem. Okay, if you change the boundary conditions, you'll get something different, right? I could mix these up in different ways. If you change the PDE, in particular this part of the PDE, if you change the way that it works with respect to x, you'll get different things as well. Okay, so for Fourier series, you have to have something that looks like, where are we? You'll have to have something that looks like this, right? If you don't get that, then Fourier series method won't work. Okay, so now I know lambda n is equal to that quantity there. So here, I can solve this for t. So we should know how to solve these. It's just going to be an exponential. E to the minus, here I'd have my mu squared, lambda n squared, and I'll have a t. Okay, so if I put these together, so that's my solution for t. So if I put these together, I can get my general solution for, I don't want it to copy all of you, just grab you, blah. That's just to save me copying and pasting. So if I put these together, I find at the end of the day, my solutions are going to be u sub n of x comma t. And this is going to be cosine. So I could put a constant here, so I will. You could drop it at this point if you wanted, but cosine of 2n minus 1 over 2 x times my exponential term. And here, my lambda n, well, that is just going to be, I'll erase all of this and then rewrite the last bit. So this is just going to be plug in lambda. Okay, so here is a family of solutions that solve the differential equation and the initial conditions, but it does not solve, or sorry, and the boundary conditions, but it does not satisfy the initial conditions. Okay, so my initial condition probably doesn't look like a single one of these cosines. It could, but if it does, then I can just match and I'm done. But now I use superposition to say u is x comma t is simply equal to the sum from n is equal to 0 to infinity. Here I'm allowing for the case where I only go from 0 up to infinity. I could go from negative infinity to infinity. You get the same things, but since you have symmetry between your sines and cosines, it doesn't matter. Nevertheless, I'll take this thing here of my c sub n cosine, well, all of this stuff. Okay. You had to drop it at the bottom, didn't you? All of this stuff here. Okay. So those are what my solutions look like. Okay. So now I need to satisfy the initial condition. So I need u of x comma 0 to be whatever that thing was. Okay. So here, if I take the terms here and I square them, they're always positive. So you chase out and you get the same symmetries, right? So if n is positive versus negative, you get the same bits coming out there. So yeah, so you can drop those. The other main thing is since you have this infinite family of solutions here, right, you only need enough of the solutions such that you can match the initial condition. Okay, so generally speaking, if your initial condition is piecewise C1, then you know if you started at 1, sometimes not. So in this case, if you started at 1, if I plug in 1, you would be starting at cosine of 1x, so that would work, given that you're fine there. If I start at 0, I get negative 1. So yeah, starting at 1 actually is probably more ideal than starting at 0, so I'll tweak it. Right? Just because if I start at 0, I'm double counting stuff, right? The whole point that I plugged in the form that I did was such that if I plugged in 1, I had a nice value. So yeah, should start at 1. Starting at 0 is also fine. But yeah, so the whole idea here is as long as you have a family here that's sufficiently nice such that you can write the initial condition that you have with as an infinite series with respect to that basis, then you're good. Okay, so here, let's just write the next line, and that'll make that more clear, I think. So here, I go n is equal to 1 up to infinity. When I plug in 0, this goes away. So I have Cn cos of 2n minus 1 over 2 times x. Right? This thing is a Fourier series. It's a Fourier series where I'm skipping a bunch of the terms, but nevertheless, it is a Fourier series. So if I compute the appropriate Fourier cosine series of whatever this thing is, I can then compare the constant terms here, the terms in front of it, and I can pull out to get my series solution. Okay, so then you just have to match with the Fourier series of, or the appropriate series of whatever your initial condition is. Okay, so in this case, it's not your traditional one because you would usually want to say in here instead of this, but it's still a Fourier series you can compute. Well, no. Sometimes it can have all of the terms. Sometimes it can skip a bunch of the terms. It completely depends on what happens, right? So if, for instance, just up here, if I replace this condition here with u of 0t, then instead of getting cosines, I'm going to get sines. And my bases for that case, I'll just write it out. If I did that replacing, my bases here, I'd have n is equal to 1 to infinity of, I'll call it Sn sine of nx. So in that case, you have all of the terms for the standard sine series. Hopefully you can see that. Hopefully it's not too small with the transition from my screen resolution to whatever yours is. But yeah, so it depends entirely on the boundary conditions. It depends on the operators you're dealing with, all of that good stuff. For the exam, it should just solve in one coefficient for the. Oh yeah, so basically in the exam, I will give you a equation that is first order in time, so you don't have to match two conditions. But if you had to match two conditions, it's really no different than matching it here. You just get two systems of equations for your various coefficients. And then with those two systems of equations for your coefficients, you have to find a solution to it, right? So here, since this is a first order in time problem, you only have one arbitrary coefficient here coming from t. If it was second order in time, my t function here wouldn't be this. It would be this plus something else, right? And you'd get a coefficient from here and a coefficient from here. You solve a system. So in theory, if I did give you a second order one, it shouldn't be difficult. You just solve this one, solve that one, match them together, right? So, but I'm not going to give you one of those. I'll give you one with one, right? And I may or may not make you actually compute a Fourier series here to actually plug it in. You'll see, right? You're going to have to compute Fourier series. You're going to have to solve this. I might give you the Fourier series here or something like that. You'll see, but be prepared to do the whole thing with computing a Fourier series and matching, right? Because you have to compute Fourier series somewhere anyways, so could be that question. So the key idea is you have to find the appropriate bases. So here you'd have to expand with respect to this bases. So you still have orthogonality conditions and all of those that modify slightly, but not really. Okay. And just as a future reference for things, if you're ever given a PDE that could differ from this, given that you can make it separable to get these two equations like this, and given that you can solve this thing, then you end up with something that you hope that at the end of the day, you hope that at the end of the day that the something that you got is an orthogonal family with respect to some inner product. Oftentimes it is, but given that all of that's true, you can do other expansions here other than Fourier expansions. So if people really care there, I can pull up my master's thesis and give an example, but yeah, you can get different families that you expand with respect to it. It's not always sine and cosine, but if things are nice, you get sines and cosines. Okay, and then it's a standard Fourier thing. Questions there? Do we feel good for this question? So like, if I was doing this on my own, you can oftentimes skip, don't skip steps on the final, but you can oftentimes skip steps. So I could, like here if I zoom out, that's not all that much work. That's showing all the details, right? Like all of the details are there, other than maybe the matching, but the matching might be like that much text, right? So just kind of intuitively, if you do these a lot, you could really skip to like these, and yeah, it's not as much work as you think is what I'm just kind of trying to get to there. Okay, so if there are no questions there, what I can do is start going through and TLDRing some of this stuff. Okay, so the definitions, I mean, I forgot who mentioned it, but I don't think I need to write out the definitions there. But definition of Laplace transform, that one's just chase out the definition, right? Existence of the Laplace transform, if you remember earlier, we had that thing where if your function is of an exponential order, namely if your function is, as time goes to infinity, is kind of acts, I don't really want to say asymptotic too, but if your function is bounded by something that looks like e to the minus mx. So if you take this, multiply by that, if this thing goes to 0 as the limit as x goes to infinity, which I really should say equals here if I'm writing it that way, so if this is true for some value of m, then you're of exponential order. That's what you need for a Fourier series to exist, right? Or for Laplace transform to exist, right? You need your f of e to the minus sx, f of x, dx. You need this integral from 0 to t. You need that to be well defined, right? If this blows up and it goes to infinity, the integral doesn't exist, so the Laplace transform doesn't exist, okay? So the only thing you need to know there is like, I could ask like, hey, is this of exponential order? And then you just go like, hey, does it look like something that's grows less fast than e to the negative mx for some value of x, right? Okay, actually positive mf, not negative. So I wrote negative, it should be positive there. Okay, Laplace transform tables. All this is asking is, hey, do you know how to read this? Right? Like, do you know how to go back and forth between these two? Okay, so there'll be questions where you have to take Laplace transforms and do things using Laplace transforms, know how to use the tables, right? Like quite literally, you could forget all of the stuff with the delta function, all of that. Well, no, it's basic property when you integrate it, but you could use this Laplace thing here to handle all of the delta things that you need. Okay, shifting theorems. Hey, these are the shifting theorems. Okay, so know these two things. Okay, so if I want to take the Laplace transform, a heavy side times a function, it's just that heavy side shifted by this thing, and not really shifted, but you know what I mean, shifted by that thing in spectral space, right? Or if I want to do this, this is legitimately shifted in spectral space. Just know these, know how to use them, and where it's appropriate to use them, right? Like if I give you a piecewise continuous forcing term, then you rewrite the forcing term in terms of a bunch of u's. You do that decomposition, you use this property of Laplace. So that's what I mean there. Like you're given those things so you don't have to memorize them. Piecewise continuous function, know what they are, right? It comes over all over the place. Exponential order, that's the thing for this existence of a Laplace transform. Just know when something's of exponential order. Kind of the classic counterexample. This is not of exponential order, but say that would be of exponential order, right? Because eventually this grows smaller than e to the mx for a value of n x for a value of n bigger than m. But in this case, no matter what you do, that grows faster than e to the x, right? That's the basic idea there. So very minimal things there. I forgot what that theorem was. Let's go review what that theorem is, because I don't know the theorems by their names, and you are not expected to know the theorems by their names. So that is coming out of Trench. So if you want to cite a theorem, you can cite it by like whatever you know it by, but if you just really want to say like, you could simply say something like, hey, the function is piecewise C1, therefore Fourier series converges pointwise. You can just say that as a thing. You don't have to cite theorems on the final. Precisely because like I don't care if you know the theorem name, I just want you to know what it is. Oh, okay. So theorem 8.1.6, that is actually the thing that tells you the existence of the Laplace transform. So that's kind of a doubling up, telling you to do the same thing twice. Yeah. You could say something like by the theorem that makes all of this make sense. You can do things like that, right? Just don't focus on memorizing theorem names. I don't care if you know there, but I do want you, like for the assignments, I wanted you to cite theorems because like it's right there. Like it's in part an anti-cheat measure, kind of a really crappy one, but it's mostly there to make you recognize why something is true, as opposed to just going like, yeah, I think that's true, therefore it is. So it forces you to understand the material at a deeper level. Okay, so Laplace transforms of piecewise continuous functions. Okay, this is the thing. If I give you a piecewise continuous function, you can rewrite it as a sum of a bunch of Heaviside functions, right? And then you take the Laplace transform of that sum, use linearity to split it up, use the shifting theorem to get rid of the Heaviside bits, and then use the tables to compute the Fourier transforms of the bits in the middle. If that, hopefully that makes sense. Like if you do this, if you have u of x times f of x, blah, plus u of x minus 1 times f of x, know how to take a piecewise continuous function, write it in this form, and then know how to evaluate this using the tables, right? Linearity, shifting theorem to get rid of the u's, so you multiply by the appropriate exponentials, and then take the Fourier series there. Okay, delta function, basically, if I give you something like y double prime is equal to the delta function of x, know how to solve that, okay? Also know that delta function has the property that f of x delta of x minus a, if you integrate this over a domain that contains a, so D where a is in there, this is f of a. Okay, so know these two properties, like that property and how to solve this. And pro tip, if you forget how to solve that, or you look at the theorem and go, God, I don't want to have to memorize that theorem, you can just take the Laplace transform of both sides. You can solve for capital Y. You can do partial fractions if needed. And then you can use the inverse Laplace transform to solve it, right? You know that Laplace transform of the delta function is this, so you can use that method to solve it, okay? So you don't have to actually memorize those extra formulas. You just need to know linearity is a thing for solutions to differential equations. And hey, Laplace transforms this, do your standard stuff, okay? So yeah, that's a thing. Using Laplace transform to solve ODEs with continuous and discontinuous forcing terms, that's really saying like, hey, are there any specific differential equation where we can use Laplace instead of? Basically everything. Given that it is a linear differential equation, you can, in theory, use Laplace transform. You can run into some issues if I give you something like x, y double prime is equal to some forcing term, right? Here, or let's just do something more complicated, f of x, and then I'll put a plus y prime here, okay? So here you can't just divide to get rid of f of x. So if you try to use the Laplace transform here, you would have to compute the Laplace transform of that. You can do that. You'd have to go to first principles, though. So I think you mean to solve where you have, so what are the two methods to solve delta function again? I think you mean methods to solve this thing where it's a delta function. One of them is there's a theorem in the text, I forgot which one it is, but it just tells you what the solution is, right? It says, hey, if you want to solve this, here's the solution where W was that 1 over the polynomial that you get from taking the Laplace transform, right? Or sorry, the inverse Laplace transform of that. So you have that. The other thing is just take the Laplace transform, solve for y, inverse Laplace transform, right? So those are the two ways you could approach it. I'm biased towards the latter, but it doesn't matter. You can use whatever you want to solve. I will double check that statement. Let me check the final. Was I a little, oh, there's the Marmy question. Was I a little mean human? I don't think I was, but in general, you can use whatever method. Yeah, I just say solve. You can do whatever you want. Okay. Well, there's a bonus mark if you fill out the things. Fine, I'll be nice and I'll just show you the one question. So actually, no, I won't show you the one question. But there is one thing that is worth a bonus mark. Okay, so it's just like previous. There is one free bonus mark on the whole thing. For the one student counting up what they need to do to pass the. or not to pass, but to barely pass with the final. Anyways, okay, so yep, Marmy's back. Also, I managed to sneak a picture onto the final. It's going to be in black and white, so the little pink nose won't show up, but there's a picture. Okay, so yeah, so using Laplace transforms to solve ODEs, this is just saying if I give you a differential equation like this, or maybe something with a discontinuous forcing term over here, can you solve it using Laplace? Yes, no. Okay, so that really, like all this Fourier stuff over here with Laplace stuff over here with Laplace transform, inverse Laplace transform, all of that comes together to do this problem. Okay, so it's not too bad. Okay, convolution theorem, that's just like, hey, if I give you f star g, can you compute the convolution interval, right? So do check the solution guide for when that one problem on assignment, I think 6, where I asked you to compute a convolution. Do check that, make sure you know how to compute it properly, but know this and how to use it, right? So basically here saying, hey, if I want to compute f star g, that's just going to be the inverse Laplace transform of the product of these Laplace transforms. Laplace of g, blah, right? So that's just take Laplace inverse here, right? So instead of computing these integrals, what you can do is you can say, hey, I have a Laplace table. If the things I want to convolute are in my Laplace table, I can get this. Then I can use partial fractions to break that up, and then find those things over here on this side of the Laplace table and go back. Okay, that's what you should know for convolution. I might ask you to evaluate an integral by definition. I might ask you to evaluate something using the convolution theorem. I might ask you to do something where I don't say convolution anywhere, but it turns out convolution is useful, right? Like convolution integrals or those integral equations, that could be fair game in theory. Okay, so all of that goes under here. Convolution applications of convolution, all that good stuff. Okay, solving constant coefficient equations with impulses. So that is literally saying do this. Oops, sorry, not that. Do this thing here with the delta. Okay, so there's a lot of doubling up here, so it looks like it's a longer list than it actually is, but I just kind of exhaustively put anything I could think of and just threw it down there. Okay, so I figured it'd be better to put too many things compared to too few. But yeah, so there's a lot of things that are combined here, like, right? Like this stuff, you need to do this. So I could have deleted that and just said there. But yeah, well, not really. You still need to know definition. Yeah. Okay, so are we good? Do we feel good for chapter 8 stuff? We have 5 minutes left, which I can extend to 15. But after that, my voice will be too dead because I have 2 hours of office hours later. So, okay. So I'm going to drink. So Fourier series. Okay, so again, really, really long list of things. A lot of this stuff collapses to like a nice little tree. Okay, so definition of the Fourier coefficients and computing Fourier series. Most things are post-midterm. So actually, I'm just going to do, it's on the sheet. Where did I say? 11 questions, 5 subparts, justify your work. Oh, I didn't say it here. I think I put it on the learn announcement. But yeah, it's the vast majority is on the newer stuff. So you need to know some of the older stuff, but yeah. Okay, so basically, can you find your Fourier coefficients? Okay, so this includes real and complex. Okay, so be able to know those formulas for finding the real coefficients and the complex coefficients. Okay, that ties in. What's a Fourier sine series? When do I have a Fourier sine series? And when I say sine, I really mean like half range, but you could also do quarter range. If I ask you about quarter range, I will give you the formulas. I don't expect you to memorize those, but know the half range expansions. Those are the standard ones. Okay, so when is it a sine series? When is it not a sine series? All that good stuff. When is it a cosine series? When is it not a cosine series? All those tricks for using symmetry to make things easier to compute, either know them or suffer and do it by brute force. Okay, so it's your choice if you want to memorize them. You can do the whole thing without memorizing any of those shortcuts, but you end up having to do things like minus pi to pi instead of 0 to pi. Sometimes you might end up having to do two integrals plus another one where the integrands are almost identical, right? One would be positive, one would be negative. So if you do that, if you do have multiple integrals that you end up splitting something into, no, there's maybe a better way, not always. Sometimes you're stuck with it. But if there isn't a better way, then know that, hey, just take whatever this is, integrate it on its own, check that thing out, and then apply it twice. Do tricks like that to save yourself time. Okay, so yeah, so know Fourier sine series, Fourier cosine series, how to compute them, all of that good stuff. Okay, know what it means to be continuous, know what it means to be C1, know what it means to be piecewise C1 and are continuous and piecewise C1. In the previous thing, I did a breakdown of these different continuities. I did it towards the end of the video. I'm not going to put little sample marks or anything like that down, but feel free to share timestamps amongst yourselves. But I do a breakdown of what these are there and how to determine them and what applies what when over there. I can redo it here if people want, but finite time. So it's choice between that or talking about the rest of the things. And again, this is recorded too, so yeah. Okay, so pointwise convergence sequence of functions. Know what this means. Be able to prove that a sequence converges pointwise to something. Not necessarily Fourier. I could give you something similar to the one that was in the text or the one that I did in class where I give you a sequence of functions and it converges pointwise to something. Know how to do that, okay? Basically, TLDR, if you want to do something like that, it breaks down to know how to compute limits. You don't have to do delta epsilon. You can just do your standard thing of f of n of x. Know how to compute this for any given value of x and say, oh, this is f of x where here's my function f. Know how to do that. Okay, so I could give you something and say, find what it pointwise converges to. I could give you something and say, prove that it pointwise converges to this, right? In both cases, in one case, you'd have to evaluate the limit from scratch. In the other case, you'd have to show, hey, this limit is equal to that, right? Calc 1 limits, okay? Calc 1 level limits, plug in a value of x. Don't actually plug in a value of x, but treat x as a variable where it's any given number, chase it out, okay? So that is there. So L infinity for continuous and piecewise continuous functions. This is cut off. It should say functions down here. So I lied. I said before this wasn't cut off. It technically isn't, but the combination of packages that are used to make this kind of in its nice thing leads to bad things. I didn't dig with it to fix it because usually the breaks worked out nicely, but here, yeah. So know how to compute this, okay? So if it's a continuous function on a bounded interval, just compute the maximum. If it's not a continuous function, but it is piecewise continuous, you might not have a maximum, but you could talk about the supremum, okay? So know how to compute that. Basically, like, hey, it gets arbitrarily close to a half, therefore the supremum's a half, something like that, okay? So know how to do this. You'll probably have a question asking somewhere to compute something like that, okay? Uniform convergence of sequences of functions. All this is saying is that, hey, instead of doing the limit as n goes to infinity, that's about infinity, of f of n minus f of x, instead of saying that this in absolute value is equal to 0 for any given value of x, you replace that with this, okay? So the maximum error goes to 0, okay? So no uniform convergence of arbitrary sequences of functions. How to show it, like that ties to Weierstrass M-test a little bit, but know how to compute those things if asked, okay? Know when a Fourier series is not uniformly convergent, okay? So for that, we had a theorem. Find a clear spot. So for that, we had a theorem that basically said if you have a sum, a sub n of x, n is 1 to infinity. If you have a sum like this and 1, this is uniformly convergent. And 2, if this also has the property that each one of these a sub n of x's are continuous, then those together imply that the sum of x, this is continuous, okay? So the converse of this says if the sum, I know this is messy, but of x, So if this is not continuous, then one of two things is true. Either one, it's not uniformly convergent, so not uniformly convergent, or two, C sub n of x, or sorry, A sub n of x is not in C. Okay, so applied to Fourier series, if the thing that the Fourier series converges to is not continuous, then since these coefficients, since all of the sine terms are continuous, that tells us that it has to converge not uniformly. Know how to do that, know how to determine when it doesn't, when convergence is not uniform. Okay, so if it's convergent, if the thing that it converges to is not continuous, then convergence is not uniform. Know that and be able to justify it basically by making that as a statement. Okay, so know when this happens, and that corresponds exactly to Gibbs phenomena. Okay, Gibbs phenomena is the lack of uniform convergence of the Fourier series. Okay, know the L2 norm for piecewise continuous functions and how to compute it, right? So you just take the square root of that integral over whatever the domain is of the function, absolute value squared dx. That's it. Pretty straightforward. So know how to compute this, know the definition. Know convergence to the mean, okay? So know what that means. Literally, this is just taking the thing that I did up here and changing that to a 2, right? That's all convergence in the mean is, okay? So know it, know the classical theorems like uniform convergence implies convergence in the mean and pointwise convergence. That's a thing. Pointwise convergence doesn't imply uniform convergence. Pointwise convergence does not imply convergence in the mean. Mean convergence does not imply pointwise convergence, and mean convergence does not imply uniform convergence. Okay, so there's not very many relations there that actually hold, but know some of that stuff mostly for the application to Fourier series, right? When is a Fourier series converge to the mean? When does it converge L2 or to L infinity? When does it converge pointwise? Know those, okay? And be able to say when it doesn't converge uniformly. We don't have a theorem for when it doesn't converge in the mean, so you don't really need to say anything there. Okay, know the periodic extension of the function, how to find it, and why we care about it, right? The periodic extension of a function is the thing that that Fourier series for that function will converge pointwise to, okay? And it'll only converge pointwise to it, no, not necessarily, but if that function is, the function that I started out with, is piecewise C1, then it will converge pointwise. So know that, right? So if it's not C1, we can't say anything. It might converge pointwise, but we don't know, okay? Know the Weierstrass M test and how to use it, okay? Know the criteria for the uniform convergence of Fourier series. So that should say series at the end. Okay. Know the convergence in the mean and know the pointwise convergence. So that theorem that has the H1, H2, H3, that's basically this, okay? So in addition to that, for the uniform convergence bit, you do want to know this thing here that if the thing's not continuous, then it doesn't converge uniformly because of this theorem here. So know that and be able to do that if needed. That's all of those. So the criteria for swapping order of integration and summation, basically you have to have convergence in the mean to be able to swap it. So know that. And here, since L2 implies convergence to the mean, L2 is obviously sufficient, but do fill in those little gaps where you do like, oh, it converges in the L infinity mean, therefore it converges in the L2 mean, therefore I can swap. Know that chain of arguments. You also need that for the current assignments, right? So yeah, know how to use this, right? So if I give you a Fourier series for something and ask you to find the Fourier series for something else by integrating it, know how to do that, okay? That's all this point is saying. So know how to do that and know how to justify why you can swap the orders of summation and integration. So the justification is just this, right? Outside of that, it's just like, hey, you integrate it. Oh, crap, I have to use Percival's theorem to compute this extra term, right? Things like that. I might give you the extra term, right? But you should know how to use Percival's theorem to find it if needed. Complex form of a Fourier series. So here I really want, can you compute the complex coefficients? Can you find the thing? You should know how to swap between the two. TLDR, if you have your AN or your CN and your SN, where those are your terms for the cos and sine, you just take the cos 1 divided by 2. That's the real part. Then you take the, or sorry, the other way. You multiply it by 2. No, divide by 2. And then you take your imaginary part and you multiply it by -1/2. or sorry, the sine part multiplied by -1/2, that's your new imaginary bit, right? That just comes from writing out that expression that I left as an exercise. Yeah, so that's this bit here. That'll be a very minutely, like if that's tested at all, it'll be worth at most 1 point for something. Okay. Percival's theorem, know it, know how to use it. Okay. You don't need it for the Fourier transform, but know it for the Fourier interval. Okay. So the big thing there that you'll probably struggle with, because I know you guys love dealing with indices on summations, right? Like all undergrads love this, right? Right? No, yeah, it's not very necessarily fun, right? But know how to swap this to a sum that looks like n equals 1 to infinity using symmetry here. Okay. Generally speaking, with Percival's theorem, you have symmetry because your C of -n is C of n bar, right? So you have some symmetry here, so you can use that symmetry to split it up. Or in the worst case, you can split it to two sums. N is minus infinity to some point, say -1, and then you could do sum from n is equal to 0 to infinity, right? Or you could pull out the 0 term or something like that, right? So know these various ways of splitting it up to branch the gap between the fact that one of the sums is from -infinity to infinity and the other one's from 1 to infinity. Okay, so definitely know that. And then the PDE one, that's the thing of know how to solve this. And that's worth, I think I said it was 12 percentage points. It's, what is it? 14, I think. Something like that. It's 9 out of that. Yeah, 14.2. 14.2% of your final is doing that. Okay, so definitely know that or how to compute that. Okay, and Fourier transform, basically know these formulas because those could be something I could ask you to state as a definition, or it could be something I ask you as a true or false type question, or it could be something that I ask you to actually compute a Fourier transform using those properties. Okay. So it's just like computing a Laplace transform from the table, but here I'm not really testing on anything other than very basic rudimentary things using those properties. So I want you to know those properties, right? So be prepared for true, false, or definition questions, or let's just say and or something where I ask you to compute them. And I could ask you to compute it by definition too. That would be mean, but I could do that. Okay, integration by parts. Yay. I think that's a good TLDR of everything. I went through it really quick. No one stopped me, so I went through it really quick. If people stopped me, I would have stopped. But that's what I mean by all of these things. That's what you need to know for them. In addition to this, one skill you definitely need to develop is the ability to do computations pretty quickly, right? So if I ask you to do a partial fraction decomposition of, ooh, that's awful, of 1 over x squared x plus 1, you should be able to do this really quickly, okay? So let's just do this. Okay, so here I'd have a over x squared plus b over x plus c over x plus 1. Okay, so Heaviside method, x is equal to 0. What does this tell me? Well, that'll tell me that a, these terms will go away if I multiply by x squared. That's going to be equal to 1. Okay, so a is 1. If x is minus 1, what does this tell me? Well, if I multiply by x plus 1, these terms go away, so it tells me c is equal to, well, plug in minus 1, 1. So I know a and c. Okay, so I can't use Heaviside method to get b, but what I can do is say, hey, I use 0 on -1. 1's not a bad number. Let's brute force that sucker. So if I plug in 1 here, I get, on one side, I get 1 over 2. That's going to be a plus b plus c over 2. Okay, I know a is 1. I don't know what b is, and I know c is a half. Okay, so if I subtract the half, subtract the 1, I get b is minus 1. Done. Okay, that's how quickly these should go. You might want to show more work for partial marks, but that's how quickly you should be able to do partial fractions with Heaviside method properly used. Do Heaviside method to cut out as many things as you can, and then deal with the fallout after you're done. Okay, not bad. Hopefully. So know how to do that. Same thing for integration by parts. Use the table, right? I think those are the that integration by parts using the table. And I think the last one would be noticing that, hey, if I have a bunch of integrals where the integrand is similar, like if I wanted to evaluate x squared e to the x, x squared e to the 2x, and x squared e to the 3x. Say if I wanted to evaluate all three of these integrals, dx, of course. Okay, so if you try to do this by doing three separate integrals, you're going to waste a lot of time. You're shooting yourself in the foot. It's going to hurt you, right? You have 2.5 hours for 11 questions. So you have plenty of time in terms of time per question. It's just that's eating up valuable time you could use on another question you're stuck on, right? So instead of doing this, what you would want to do is do something like just notice e to the ax dx. Okay, I can do this using the tabular method pretty quickly. And then I can just plug in the values 1, 2, and 3, and I'm done. Okay, and again, tabular method, just to show how quickly that actually works out. X squared, 2x, 2, 0. Here at e to the ax, I integrate, so I have 1 over a, the same term, 1 over a squared, the same term, 1 over a cubed. I know it's getting squished, the same term. Plus or minus 1s, okay? So plus, minus, etc. So if you chase this out, here I would get this. So I'd have 1 over a, there's going to be e to the ax in front of everything. So 1 over a x squared plus 2 over a squared, not a plus, but a minus. Alternate sign, 2 over a squared. Here I'd have my 2x, so I have 2x over a squared. Okay, that's that term. So done with that. Next, I get a plus again, 2 over a cubed. That's it. Okay, so it's kind of squished on the side, but I knew which terms were sitting where, so I don't really need it. But that's how quickly you should be able to do these things, right? Not necessarily, right? You can struggle a bit. If you can't do that, it's not a bad sign that you're going to do bad. But if you can do that, it increases your ability to increase the probability you'll do well, purely because you'll have more time, right? So yeah, just practice those skills. If you don't have them, it's fine, but practice them and see, put yourself in a better position, okay? And it shouldn't take too much to do that. Let's see, yeah. And for these type of things, you can actually Google something like Paul's online notes or something like that. And you can find a bunch of examples of doing partial fractions, right? That's something that's readily available. Same thing here for integration by parts. You can just look up a Calc 1 text. There's going to be lots of examples. So you can get your practice there. Okay. I'll cut it off there. Are there any questions? No one interrupted me, so I just kept going. No questions. We're all good. Okay. I'll probably be putting, with probability 1, we'll be putting another 2-hour, something like that, review session on Friday where I'll go through things. I'm still picking down the time, that type of thing. I have a couple meetings I'll have to work around, but I'll avoid, I think it was 12 to 1, because I believe you have a review session then. So I'll avoid that bit, but I'll put some period of time there. If you guys want, if people have a very particular preference they want, you could open up a Piazza post, put preferred time, something like that, and I'll work around those. If there's conflicting bits, if you guys take that route, then I'll put up a survey, or not survey, like a poll for you guys to decide. Otherwise, I'll just be a dictator and pick a point time. Okay, are we all good? Guys are being quiet. The thing that sucks about the online bit. Okay, so I'm going to go ahead and stop the recording so it can start finishing up there.